for the invitation. So I changed the title a little, just in order to have the word period appear in the title. I hope that's okay with you. This is joint work with Spencer-Bloch and Emre Sertöz, who are both here in the audience, so I count on them for correcting the mistakes that I will certainly make. And this story started out with a conjecture that Spencer had a couple of years ago. And I just want to start out by telling you about his conjecture. So this is the setup. I will work with varieties over Q. Okay, in reality you can work over number fields, and certainly soon enough you need number fields for some objects that I will introduce, but just for the sake of exposition, let's pretend number fields are Q. And let's take D, a non-negative integer. It is perfectly fine to take D as 0. That is already an interesting case, and will take up, actually, will be the content of our theorem in the end. And he started out by considering x0 in P 2D plus 2 a hypersurface with exactly one node. I say with one node, but I mean exactly one node, and let's call it n. And then you can do two things. One is to blow up the projective space. So this is the blow up in n of projective space. And in there you can look at y, the strip transform of x0. And this is then a smooth projective variety over Q. And it contains Q, the exceptional quadric. And this sits naturally in some projective space one dimension lower, 2D plus 1. And this exceptional quadric is a smooth, even dimensional quadric. And, well, 2D dimensional to be precise, and it has two rulings, lambda 1, lambda 2 in Q, rulings, or I say take elements from these rulings, and there's certain moving systems of projective spaces inside Q, and take their difference, lambda. And I view this as a cycle on Y. Algebraic cycle on this smooth projective variety Y over Q. Okay, lambda 1 and lambda 2 need not be defined over Q, but we pretend that all number fields are Q in this talk, so. But yeah, of course, we should work over number fields instead of over Q. Then the other movement you could make, starting from x0, is to look at a smoothing deformation inside P to the 2D cross S over some base variety S, which we take to be a smooth curve, everything over Q. So the S is also over Q, and it has a distinguished base point, over which the fiber is equal to be, is said to be x0, and this is a smoothing deformation. Smoothening deformation of x0. And then we enter the world of variations of Hodge structures and maybe limit mixed Hodge structures. So we center over C everything, and we get a variation of Hodge structures over S. Well, the complex numbers, the complex points of S with fiber. The middle cohomology of the fibers in this smoothening deformation, H2D plus 1 XT Z.
Sorry?
Yeah.
What do you mean by smooth curve? So 0 in S?
Yeah, so 0 in S is a point, and the fiber over S over 0 is this x0.
Ah, so this is just the name of the point. Ah, okay.
Yeah, sorry. Yeah. Maybe like this. So X is total family we assume to be smooth. And yes, such things have limit mixed Hodge structures, but for that you have to fix a cotangent vector or a tangent vector at the origin, non-zero. Let's say a cotangent vector. Everything's still defined over Q, so this is the arithmetic information in the right-hand side, and we get a limit mixed Hodge structure, and we call it L chi, and it is a mixed Hodge structure of a special type. It is called a biextension. I will give definitions later on. For those who haven't seen such mixed Hodge structures, it's a biextension, maybe up to a Tate twist. But this is just a technicality. Not really important.
I read this as L chi circle. What does it belong to? Is it the thing above, the thing next to it, or it's just sitting there?
It is a element of the category of mixed Hodge structures.
No, but physically, is it attached to omega 0 S1? It's just
It is attached to this family and chi.
So it's just a separate thing. It's not
It's the limit
omega
image. It follows the line limit image is
So L chi is the limit mixed.
Yes.
Yes.
And is it critical to have a rational point in this case?
Well, I'm going to compare this object with the object on the left-hand side. So I want to store some arithmetic information even on the right-hand side, even if this looks completely complex analytically. So this chi is also to be defined over Q. And then the question that Spencer-Bloch asked is, to what extent do lambda and L chi know about each other? So in the course of our work, we have been referring to the left-hand side sort of as the intrinsic picture in x0, so you're searching in x0, and the right-hand side as being the extrinsic picture, so you unfold or you smooth the node, and you see in retrospect what you can get by approaching the node again. And the conjecture that he formulated is that up to an element of Q times log absolute value of Q star, the height of lambda L chi are equal. Of course, I have to tell you what these heights are. These are certain real numbers that one can attach apparently to this cycle on the left-hand side and this mixed Hodge structure on the right-hand side. I will tell you about it, and they should be equal, he said. But note that lambda is already, I mean, its height is what it is, but the mixed Hodge structure still depends on the choice of the chi, the deformation parameter. So, but if you change the chi by an element of Q, so you replace it by A times chi, where A is a non-zero rational number, then this height, whatever it may be, will change by the log of the norm of A, and that is inside this group. So that's okay.
So usually when one has global heights in the curve, there's kind of an Archimedean and non-Archimedean part, and if you change the choices. So is there a way to normalize, I mean, just on the right-hand side, to normalize L chi so that there's no ambiguity of Q log Q?
Well, yes, indeed. But
you
find another invariant of chi, and you subtract it from L chi, and it's going to be some norm of chi, and there is some arithmetic model of this bundle, omega 1.
Yeah, but you know what that thing is. So
Yes. Yeah, there's a way to normalize.
And then it's well defined as the conjecture then that they're equal, or is there still some ambiguity?
I will come to that.
May I have another question?
Sure.
This is a nodal singularity. In general, you expect that for more complicated singularities, something like
This is just the first starting case of investigation. It was already hard enough, but more nodes or more worse singularities, okay, you can ask, but it's not yet time for even a conjecture there. We have no experimental data for that. And, so just keep with this very simple situation. It is indeed geometrically very simple, but arithmetically it turns out already to be rather subtle. So, okay, so I'll leave the suspense for Don now. Write the results later, but just tell you a bit about heights of cycles and heights of mixed biextensions. So that will be my two next paragraphs. Of course, I cannot give a course on this in this time frame, but let me just give you the idea. So let's work with V is to projective variety. Over Q again, geometrically connected. Again, you can work over a number field. And take Z and W cycles on V. I'm just sketching ideas. I'm not going to be very precise. Algebraic cycles on V. But it is important to ask that they are homologically trivial. So if you pass up to the complex numbers, then in homology of this topological space, this manifold, they are supposed to be trivial in homology. So for example, if V would be a curve, and in fact curves are in our scope, if D is equal to 0, then x0 is a nodal curve in P2. And also y is a curve. Actually, this is interesting because the exceptional quadric is going to be 2 points in P1. So there will be 2 designated points, and that is, of course, has to do with the decentralization of the normalization of this curve. And on a curve, homologically trivial means that the degree of your cycle, of your divisor, is 0. So, in fact, this lambda here is homologically trivial, at least if the degree of the hypersurface is big enough. I think at least 3 will already work. And so we want them to live in certain dimensions. So say Z is all its components have dimension D. And for W, let's say that all its components have dimension E. And ask that D plus E is the dim of V minus 1. This is the correct numerology in order to get some kind of intersection pairing between these 2 cycles. And also that condition holds for our lambda, where, so e.g. take V is W is lambda, and D is in fact equal to E in this case. So it's kind of in the right dimension in order to take a self-intersection, and this self-intersection is going to be related to the height. So up to some standard assumptions, about models over the integers of V, one has a canonical so-called Beilinson-Bloch height pairing between these 2 cycles, and it is a real number. And the idea behind this number is that you can spread out V into a proper, regular, flat model, calligraphic V over Z. We don't know if such things exist in general, but in many good cases we do know. And likewise, spread out the cycles into some cycles over calligraphic V. So let's say calligraphic V, calligraphic W over V. And I want to keep the dimensions, so this is still to be taken in the chow. But now D plus 1, sort of if you add the arithmetic dimension, you add one dimension. And there's an assumption you want them to be orthogonal to all vertical cycles in this model. So vertical means that the push forward to the integers is a closed point of the integers. So there is no intersection with the generic fiber, which is V. Yeah, it's standard assumptions that such models exist and such extensions exist. So this is a kind of mimicking the condition of being homologically trivial, but now on the finite fibers, at the finite places. And this was introduced in the early 80s by both Beilinson and Bloch, about the same time. And once you have these extensions, you put the height pairing to be defined by the intersection of these arithmetic cycles, but in the sense of Gillet and Soulet. So this is arithmetic intersection theory. And no further data of the generic fiber or some Green's currents or whatever, no further choices of data is needed. If you have this setup, you have this number. And the interesting case for us is when D is equal to E. For example, Z and W are equal. Let's indeed ask that. We set the height of Z to be essentially this self-intersection. And we want to modify this by the sign. And the sign is there because of arithmetic standard conjectures of Hodge index type that will say that this number here, the self-intersection, is supposed to be non-negative. And that's what we would like for heights. So that they are real numbers that moreover are non-negative.
So if you have a model that doesn't allow the scheme to be this kind of, can you take out right spaces, okay?
Presumably, but let's not get in that direction right now, okay? I think you want difficult things, whereas we are dealing with very simple situations. And an example which is important also later for us in the theorem is the case that dim V is actually equal to 1. And then all this works. And so remember, Z and W being homologically trivial just means that they are degree 0 divisors. So I have two divisors of degree 0 on my curve over Q. And apparently there is a real number canonically attached to this. And this is already done much earlier in the 60s by Néron-Tate. So this is basically minus the Néron-Tate height pairing. Of what? Well, you could say of the divisors Z and W, but in fact you can work on the Jacobian of V, and take their classes. Yeah, and usually the theory of Néron-Tate is done in the context of Jacobians, so more generally abelian varieties with a polarization. And then it is the Néron pairing there. So you take their classes. In the Jacobian of V. And certainly by now Z and W are defined over some number fields over Q bar, and these are elements of the Q bar points of the Jacobian of B, and they have a canonical pairing, and it coincides with the Beilinson-Bloch pairing in this case. And in particular, when Z and W are equal, the height of Z is therefore, because the sign there is also a minus, it is going to be the Néron-Tate height of the class of V, which is indeed non-negative. So this is an important special case of the Beilinson-Bloch height pairing. So that explains the height on the left-hand side. Now let's move a little to the right-hand side, doing this variation of pure Hodge structures and taking the limit mixed Hodge structure. First, let us talk about what is this biextension thing. It's maybe not generally known, but I will explain that biextensions are all over the place. So let H be a pure Z Hodge structure of weight -1. Then a biextension of H is a Z mixed Hodge structure B with an identification of the graded pieces, so W of B, with the following standard, so Z1. So this is weight -2, and then there's H, which is the weight -1 graded piece, and there's another Z, which is the weight 0 graded piece. And you see here that I'm taking the weight graded to be, or the weight grading to be in terms of Z modules, not Q vector spaces as usual. This thing can be done over the integers. And let's say that B of H is the set or the moduli space of biextensions of H. We want to sort of classify them. And the first remark is that you have a map to two other mixed Hodge structures. The one is the extensions of Z by H, and the other is the extensions of H by Z1, because you could pick up your B and you see from the structure that you get two extensions. The first is W0B mod W minus 2 of B. And the other one is just the -1 weight part of B. So this is a biextension, and they have heights, and this height is a bit difficult to define, although there are many ways to define it. They are all rather intricate. But what you could, the shortest one I think is to say that working with the associated R mixed Hodge structures, so that means you replace the role of Z by R, so it is a certain R vector space with a R weight grading, and then on the complexified space you have a Hodge filtration. So we work with R mixed Hodge structures, and then these extensions you can prove they are necessarily trivial. And that means that if you tensor B with R, then you have a canonical splitting into a piece, let's call it G, and our original pure Hodge structure H, tensor with R. So this means tensor with R, usualization. And this G is an extension of R by R1. And this is canonically isomorphic to R. And the height of B is the resulting element of R here in this canonical identification. And just for intuition, it is also good to give a little bit more details about the structure of this map here. I mean, this is not just a set theoretic map, but you can endow it with a little bit more structure by observing that these two are certain complex tori. This is the Jacobian. If you think about it, if H would be the Hodge structure of a complex, compact Riemann surface, this would definitely be the Jacobian. So we denote it by the Jacobian of H, and this would be the dual of that Jacobian, or the Jacobian of the dual Hodge structure, but then you work with two twists. And these things are complex tori. Just as the ordinary Jacobian of a complex Riemann surface is a complex torus, and they are dual complex tori. And whenever you have dual complex tori, you have a Poincare torsor over the product. And this map here is exactly the structure of a Poincare torsor. So B of H is the Poincare torsor. So it's a GM torsor over this Jacobian. It's dual, and that is maybe important for intuition later on. Now this is highly abstract, and we want to be able to compute heights of biextensions whenever we find them in nature, and I will tell you later that we can find them in nature a lot. So maybe there's a way to compute them from very concrete data. For example, a period matrix. I mean, we are used to maybe period matrices for Hodge structures, but also mixed Hodge structures have period matrices, and especially biextensions have period matrices. So from a period matrix, we want to find an algorithm to compute this height, and this is part of what we did in our work, to present such an algorithm. So now come the periods in order to fit in this conference. So how does this work? We have a Hodge filtration and a weight filtration, and we want to see how they talk to one another and express that in terms of a matrix. So let's say that omega 1 of 2 omega k plus 1 are in the zero piece of the Hodge filtration on B. And then we take some elements in the underlying lattice of B, namely gamma 0, which we take to be 2 pi I in Z1. Then some elements, gamma 1 to gamma k, 2k, that are sent to a basis of the underlying Z structure of H. And then there's one final lattice vector that we send to the one in Z. Yeah, so kind of you see that we have a matrix now of B, which has this structure like here we put the gammas, so this is 2k plus 2, and here we put the omegas. And this is k plus 1. So the dimensions are 2k plus 2 and k plus 1. And it is now set up in such a way that this vector here is all zeros. Here there will be a 1. here there will be the period matrix of the Hodge structure H, and the rest, yeah, something. Yeah. So this is a period matrix on these data of my biextension, and the claim is, so kind of between brackets, we can get the height of B from PB, from any such period matrix by some algorithm that we describe in the paper. The papers are on archive. 2 papers on archive.
Can you add the HIN?
Maybe it's too late because they are also published now. I'm sorry about that.
Still add to the archive.
Good. So let's look for some examples of biextensions. I already said in my setup that there will be some biextension. Maybe I'm trying to keep this setup for a moment. Okay, some biextensions that we all like. Example 1. So V and Z and W are as above, so variety and then cycles Z and W. And now ask that they have disjoint support. This is now an important assumption for the moment. So these cycles Z and W have disjoint support, and then we can consider an associated mixed Hodge structure, BZW, which is the H to the plus 1 of V. Of course, I need to take the complex points now of everything, but I will suppress that. Relative cohomology of the open part, V minus Z, with respect to W, and then maybe some Tate twist. ZT plus 1, I think. And this can also be written by symmetry. This thing is symmetric in terms of relative cohomology on V minus W, and then I take Z here, and again Z coefficients, and then the Tate twist is by E plus 1. So, yeah, so kind of the topology gives you the extensions, yeah, so maybe a relative cohomology of V and W, and the cohomology of V minus Z. This is where these two, where this mixed Hodge structure are the two extensions here. So they can be understood on a very topological level. And these are biextensions. So that is the claim, these are biextensions. And moreover, the height of this biextension is supposed, and then I answer Gonzague's question, is supposed to give the non-Archimedean, the Archimedean contribution to the Beilinson-Bloch height pairing of Z and W. So Z and W were still in the correct dimensions in order for them to pair. And in fact, this works for, again, curves. We know unconditionally that this kind of setup works for curves. And then this Poincare torsor, of course, is the usual Poincare torsor over the usual Jacobian of my curve, and everything is in fact algebraic. So in reality, in general, these complex tori are not algebraic, but in this case they are, and also the biextensions in the Poincare torsor are algebraic elements. So that means that algebraic and arithmetic geometry applies. Yes, so there's an algebraic element of the functorators or over the Jacobian cross its dual. And from this algebraic setup, then indeed, as Tom Jagget suggested, you can sort of, because it's algebraic, you have Archimedean contributions, but also natural contributions from the finite places. I'm not going into the details of how they are defined, but think of a kind of intersection product. Yeah? The finite places, these Gillet-Soulet and Néron-Tate pairings are essentially given by intersection numbers. It's not the whole story, but essentially that is what it is.
Yeah. This is only in the one-dimensional case.
This is the one-dimensional case, and everything works.
So, very briefly repeating my question, you say it's supposed to be, which I assume it isn't proof, but the question, not is there even conjecturally in the higher dimension? Yeah. Extension, but the biextension also has some contributions from finite terms.
Absolutely. Conjecturally there is, and they are explained in the paper by Beilinson, and later works have given conjectural expressions for the local.
So there's a kind of an extended height that includes that, which would be
Exactly. Yeah.
and the CW, not just the Archimedean. Okay, just assume that was.
Yeah, and the pairing between ZW is kind of a sum over all places of Q, or my number field, of course, in reality. So the primes and the infinite prime of some log of norms, and maybe of this algebraic element, kind of. So you can take, even if, because it's algebraic, I can sort of also take the p-adic norm. You can make this precise, and these are the local neuron pairings. So we're kind of at a situation where some Archimedean construction using intermediate Jacobians and Hodge structures is known, but we are sort of not yet, it's not clear yet how this works over the non-Archimedean places. And you definitely want to have such a theory in general, but it's not known yet, as far as I can see. Okay. Maybe get a sub-example of this one. I will actually write down a formula, because that is also kind of in the spirit of this conference. Make things more concrete. In the case of curves, then V is equal to 1. So still working with the dimension V equal to 1 case, I have a sub-example. Very basic case. C is just a difference between 2 points. Same with W. And then attached to this, I have this omega, W1, W2, the unique rational differential with whose residue divisor is exactly W. Yeah, so it has a residue plus 1 at W1, residue minus 1 at W2, and is holomorphic everywhere else, and purely imaginary periods. This time I was earlier than Tom. Okay, then the minus log of the norm of this biextension, just fancy terminology, is the height of this biextension, can be computed as being the real part of the integral, the line integral from z1 to z2 of this omega. Yeah, and now we are getting really into mixed periods of the very simple kind that we all like. And yeah, maybe I'm not going to write it down, but if you even specialize further to the case that the curve is P1, then I have 4 points, and this height is the log of the norm of the cross ratio. Yeah, so it is a kind of elementary number, but still kind of subtle, right? I mean, you have to do something with these 4 points that is kind of invariant, and it's the cross ratio, of course, and indeed, that turns out, pops up here in this setup. Okay, so this is the case where the cycles have disjoint support. All is nice, all is fine, especially on curves. But note that here we are interested in a self-intersection. So this setup is not applicable directly. And you are looking for a kind of regularization procedure, yeah, in order to make sense even of self-intersections using this technology. And that's kind of what we are looking for. But it's not there yet. But we have the limit makes such structure, yeah, the extrinsic picture, and that gives me the second example of a biextension. So let L chi within our setup. Still the same limit mixed Hodge structure. It is a biextension. And let me explain this to you in terms of period matrices. In the case that D is 0, so that means that we are actually talking about a nodal curve that is whose node is smoothened out. So let me attempt making a picture here. So this is my x0, and the typical fiber of the smoothing is here. And recall that this x0 is normalized, still on the board. So this node here comes from 2 points, P and Q, let's say. And P and Q are identified to be this node. Yeah, so modeled out by P Q. So this is Y in the picture. So this is now a deformation. So here is 0, here is T. And we kind of let T move to 0. And we fix this differential at 0, and let's set it to be equal to the D of T. So T is kind of a rational algebraic parameter. And the period matrix, let's say, of the so the variations of Hodge structure, that is here. So these are the pure Hodge structures, genus 3 curves. So they look like line integrals, gamma j's, mu i's. So here k plus 1 in this picture is the genus of xt in this picture. So so the general setup is that this is the basis of f d plus 1 h2d plus 1 xt z. So this is in the general higher dimensional case. And these gamma j's our basis of homology. Homology 2D plus 1 x2. And yeah, so this situation is geometrically quite classical. And there is Picard-Lefschetz theory, and there is vanishing cycles, there is co-vanishing cycles. So kind of here we have, oh, this chalk is not good anymore. Anyway, so here is a vanishing cycle, vanishes into the node, and we have a co-vanishing cycle which survives. But this co-vanishing cycle, from the point of view of y, is rather bad, because here it becomes a line segment from P to Q, but maybe some of these holomorphic differentials degenerate because the genus here is smaller, so there's not enough room for all these to become holomorphic. And indeed, some of them will become one of these standard midomorphic differentials on P and Q. But then this line integral diverges, yeah, because P and Q are poles. Yeah, so it is clear that this period matrix is going to diverge. But the limit mixed Hodge structure sort of cancels that divergence in an intelligent way. And on the level of period matrices, that is done as follows. We can show that P of T is some bounded holomorphic matrix in terms of T plus log T over 2 pi I times this matrix, which is zeros everywhere except in the down left corner. So this will indicate the divergent part. Yeah, because in fact we can set things up in such a way that the mu g, so the mu k plus 1, degenerates into the omega of t comma q. And then it will diverge, and then the limit mixed Hodge structure can be described by its period matrix, and it is going to be the value at 0 of this matrix P0.
And just a question, in the original context, there was a weight filtration to the 3 pieces.
3 pieces.
But in this case, 2 pieces. So what's...
No, in this, maybe you're, no, I will show you now the structure of this period matrix. I will tell you. It is indeed of the correct shape. The 2 pieces that have to do with the Z1 and the Z have come from the vanishing and the co-vanishing cycle in this period. So let me call them alpha and beta. Alpha is the co-vanishing cycle, and beta is the vanishing cycle.
Sorry?
Yeah.
You wrote it, B is 0 in this case. So,
What did I write?
base B0.
Oh yeah, for the picture.
I just do a picture.
For the picture, but this setup is more general.
Okay.
So in the picture, k plus 1 is g of that fiber.
Your situation is 0 means that you have x0 and x2, right?
Sorry?
Yeah.
D is 0 means that x0 is one dimensional.
Also, it's a Riemann surface. Okay.
And y is a Riemann surface.
Okay.
Is this here? So D is the dimension of lambda, kind of. So, yeah, so the period matrix, well, it's a finite matrix. And indeed, here you get zeros, and here you get a 2 pi I. 2 pi I to the D, maybe, D plus 1. In the general D case, so that means that you have to make a Tate twist in order to arrive at a biextension. But let's not care about these technical details. Here you get the period matrix of the H1 of the normalization of the nodal curve in the central fiber. And so these are still parameterized by mu1 to mu k, but sort of the last bit is kind of this meromorphic differential, omega p minus q. So here was an interesting number, which is kind of the deregularized integral of z e to q of this omega of pq with regards to the coordinate t. And here is some stuff that, and if you choose omega again carefully with these imaginary periods being 0, then in fact it also becomes 0. So you can simplify this a whole lot. And the idea is that you think of this number here as the regularized divergent integral. With respect to the coordinate t. And then the conjecture of Spencer-Bloch is the following. In our setup, height of z, height of lambda is height of L chi in R mod Q times log Q star. So that was the conjecture. Now let's go to results in the last 5 minutes. So actually Beilinson in lectures in June 21 and also on archive in August 22, he proves the conjecture of Bloch, but he made some motivic assumption in his proof. It's sort of kind of standard motivic assumption. Anyway, standard assumptions have been around for defining these pairings anyway, so that's not too bad. So, okay, fine. Good. I mean, this is on archive, maybe not with HIM stamp on it, but still. And yeah, so 21, 22, proof. But now, indeed, as Gonzague would ask, can we do better? And get some equalities in R. And indeed, this means that you would have to find another way to incorporate this choice of chi. We can do that, and then make this height L chi into something invariant. That's okay. And then you would like to lift this equality into equality of real numbers. So in some sense, make the heights explicit.
But you did it differently, right?
Rather differently, I would say, yeah. So this paper is completely in the motivic context. Motives, Hodge realization, six-sphincter formalism, vanishing cycles, sheaves. Anyway, for me at least, it's a bit too advanced.
It's very Beilinson.
Well, I'll leave that to you to comment. So we got a result for curves. So dim V is 1. I will not write down, maybe in the interest of time. Maybe, well, I'm erasing, thinking of how to present this in just 2 minutes. We'll be fine. I can at least explain to you how we get the result. get a result precise. We get an identity in R for D is 0. So this is our result. And the idea, in fact, a lot of the ideas I have already presented on the blackboard. So the Kodaira-Spencer map gives an identification between omega 1 and 0 and the omega 1s at these 2 points. This is a canonical isomorphism. Now I can use this chi that we took to pick local coordinates about P and Q, such that chi corresponds under this Kodaira-Spencer isomorphism with du tensor dv. Then I can consider regularized local neuron pairings. This idea goes back to an article of Gross in the Cornell-Silverman volume in arithmetic geometry. So this would look like something like the following. For all mu, place of q, or of my number field, let's set z, so z is p minus q, regularized with respect to chi, to be a limit. The limit is taken in the nu-adic topology. P prime goes to P, Q prime goes to Q. Of what? Well, it's gone, but when we have disjoint degree 0 divisors, we have a perfectly well-defined local pairing, the local neuron pairing. And we take it, but of course, as the points P prime and Q prime move towards P and Q in the nu-adic topology, this is going to diverge. But we know the divergence. The divergence can be controlled in terms of these local coordinates. And this is what we set. And then if you set this, we have a local to global formula. Which indeed writes the global height as the sum of these local heights, local regularized heights. So that's good. In fact, also this goes back to the paper of Gross. But then we observe that for the infinite place, the Archimedean place, well, we have seen this formula for this local neuron pairing. It's still there. Real part of this integral. Yeah, so it turns out to be z infinity chi is lim p prime to p, q prime to q, of this real part of this mixed period p prime to q prime omega p q minus log u p prime to q prime. Okay, but now morally speaking, this u times v is exactly chi, yeah, or dt in my extrinsic picture. Yeah, so you just stare at it and conclude that this is the height of L of Chen. So that means that the infinite part, the infinite regularized pairing, is the height of the limit mixed Hodge structure. So the task is to understand or write down a formula for the regularized pairings for the finite places. Yeah, and maybe this is already explicit enough for you. It is sort of clear that indeed this contribution gives rise to an element of Q times log Q star. But using models of the curve over the integers, you can even go further and make this even more explicit in terms of Zariski closures of P and Q over the model, some intersection theory on the model. And just to finalize this talk, just to finish this talk, the formula is so explicit that you can actually put it into a computer. In fact, Emre has a very nice method of computing limit mixed-art structures of variations of hypersurfaces. And so these numbers height of Lk chi can be computed efficiently to a very high precision. So in principle, with this theorem, you get a method to calculate Néron-Tate heights on curves. So we did that, we couldn't help it, and tried. And this works against known methods for calculating heights on curves. These methods are better, the other methods are better, but still it's an interesting point of view. So that's okay, and then because we want to understand the higher dimensional case better, well, there are many approaches one could take. I mean, there's Beilinson's approach, but for me at least that's too hard. And you could say, well, there's the numerical approach. First, let us get some numbers. Yeah, so, and we did that. We started with a cubic threefold. There's a beautiful geometry there, connecting this to genus 4 curves, sextic space curves. Do some calculations there, and you get exactly the expected contribution in this group. So that is encouraging. And on the theoretical level, of course, we are looking for an extension of this argument to the higher dimensional case. But there are many subtle things that just work because we are dealing with curves. And we have no idea yet how to generalize this to higher dimensions. So, thank you very much for your attention.